tonight.
Thanks. So thanks, Mike, for the introduction, and thanks everyone for coming on a cold-ish winter evening. Can you hear me well? Yes. Okay. So the first thing I want to say, if you listen carefully to the title of my talk, as announced and as I sent to the organizers, it said monster black holes at the edge of the universe. Then I was given this slide to put up, and magically this became the center of the universe, and I was going to make a big fuss and complain and say we should correct it because this is not what I sent you. But then I realized I can use this to make a point. Of course, the universe has neither an edge nor a center because it's the same statistically everywhere. So then I can clarify what I meant by the edge of the universe in a second. But by way, let me switch to the actual talk. So this will be a maybe slightly unusual talk because I will tell you something that is very fascinating and interesting. We have these very large black holes in galaxies in the present universe, and we figured out relatively recently that they've been there for a long time. And I have to explain to you why this is surprising, and then I won't be able to answer how they got there. I can just tell you the most current best three ideas, and then you can go home and think about them. So I want to start by saying everybody seems to be fascinated by black holes. Black holes have very different views for physics. As emphasized, I'm in both physics and astronomy department. So physicists have a picture of a black hole like this. It's very simple. It's some point mass which distorts space-time. Astronomers think of black holes much more differently. It's a much richer, it's a live thing. We know they are out there. They're surrounded by plasma, and they shine, and they grow, and we have to understand how they evolve, etc. So that's more the focus of this particular talk. Actually, let me start with a question. Well, let me since I made this point, let me just clarify. So as you all know, the universe doesn't have a center or an edge. This is actually a picture of all the galaxies cataloged by the Sloan Digital Sky Survey. So every point in this image is a galaxy, and this is a slice on the sky. So we're looking at two coordinates and two angular coordinates in the plane spread out here, and the point here is that we are here. We are located at the center of this picture. The universe looks the same everywhere, but then as you go farther and farther, you do see some evolution. So we see galaxies out to roughly 13, so long ago that the light took more than 13 billion years to get here. That means we're seeing the picture of the universe as it was 13 billion years ago, which, as you probably know, the age of the universe is 13.8 billion years. So this is something like the first 2% of the age of the universe that we can get out to. The deepest images are actually not by this big Sloan Digital Sky Survey. It's a much deeper exposure by the James Webb Space Telescope, which extends over here, and the record holder galaxies at this particular look-back time of 13.4 billion years. So when I said my original title, Black Holes at the Edge of the Universe, what I meant is if you peer with your telescopes the farthest possible distances, which is the furthest possible look-back time, the edge of our observable universe is where we find some black holes, which I'll discuss. Now, just before I get to scientific things, I like to ask one more question from the audience, which is, how many of you know who coined the term black hole? Only one person?
Fred Hoyle has a comment against the idea of
so that's warm. Fred Hoyle's comment was actually the Big Bang, and was a comment against the idea of the expanding universe. If I actually ask the same question in my physics colleagues, and they usually say, well, it was we all know it was Jordan Wheeler, professor in Princeton, who's actually passed away in 2008. This is John Wheeler, and he's universally credited coining this term black hole. But I read his autobiography a few years ago, where he said the following. In 1967, Vittorio Canuto, who was the head of NASA's Goddard Institute for Space Studies at 2880 Broadway, invited him to a conference. Then he describes, at this conference, he talked about pulsars. Possibility that at the center of a pulsar is a gravitationally completely collapsed object. I remarked one couldn't keep saying gravitationally completely collapsed object over and over. One needed a phrase. How about black hole? Asked someone in the audience. I had been searching for the right term for months, mulling it over, bathtub, blah, blah, blah. Suddenly this. So in fact, in his biography, he says this is an anonymous person. And I actually tried to find out who this person was, because this office, this GIS, is still there. And just to amuse you, this is the view from my office at Columbia. This is, you're looking downtown, this is Broadway is here. Then you walk on Broadway. And this is 2880 Broadway. And this building, so everything above this Tom's Diner, this is GIS. So black hole was born somewhere there. So next time you see tourists taking pictures, just tell them to turn the camera. And the black holes are more interesting than Seinfeld. Okay. So with this clarified, so as I mentioned, physicists think of black holes in a simple fashion. It's something that distorts space-time. This represents curvature of space-time. I think probably everybody here knows that there is something called the horizon. So if you find yourself at some space-time point down here, you can never come back out. And physicists ask various questions about black holes. And I'm just laying this out so that I can show you the difference for astronomers. But basically, this is a prediction from Einstein's theory of general relativity. Gravity pulls arbitrarily large masses to a very small region, and space becomes very curved. This was actually mathematically found by Carl Schwarzschild in 1915. He solved the equations by Albert Einstein. He was actually doing that while serving in the First World War on the Russian front. And I already mentioned this horizon, which is fascinating that you cannot come out. Physicists ask questions like, what exactly happens in the middle of the black hole? What happens to things which fall in the horizon? Does the information completely disappear from our universe? And even whether general relativity, which gives rise to this notion, is it a correct theory of gravity? Now, some physicists also care to ask the question, do they actually exist, or is this a mathematical solution of Einstein's equations? Does nature actually realize these solutions? Is a good question. Astrophysicists think of it very differently. We think they definitely exist, and we now have ample proof, which I'll show you in a second. But as I mentioned already in the introduction, the black hole is not alone usually. The swirling stuff of either we call it plasma or gas, which is falling into the black hole, and it's moving very fast. It heats up, and it actually gets really, really hot because of the friction on itself as this gas falls in and emits bright radiation. Now, in terms of the observations of black holes, we know that there are, as I said, they're kind of ubiquitous. First of all, we know that stars, if they're larger than the sun by a factor of 25 or more in mass, then when they die, they exhaust all their nuclear fuel, then they collapse into a black hole. This is well understood theory of stellar evolution. And in fact, observationally, we also see stellar mass, these are so-called stellar mass black holes, few times the mass of the sun. I mean, just as an aside, we actually only discovered these black holes. They're obviously black. But if there's something nearby, another star, as shown in this cartoon, then the star can be tidally distorted and material ripped off from the star and fuel this black hole, which then shines brightly in X-rays. So this has been known for decades, and there are dozens of such things called X-ray binaries in our galaxy. I should say our galaxy should have about 100 million of these small black holes, because roughly 0.1% of all stars have this large mass, and when they die, which happens relatively quickly, much shorter than the age of our galaxy, a few million years as opposed to billions of years. There's generations of stars which have died, and there's 100 million of these black holes, but we only see a few dozen. The other way, I'm sure we've seen these small black holes, is if they collide. If they come so close to each other that they spiral in and merge, they distort space-time in a dynamic fashion, not a static black hole fashion, because they're moving around. These are called gravitational waves, and I'm sure, again, most of you know, they were discovered 5 years ago by an experiment, these gravitational waves. So we know stellar mass black holes exist. We have an idea of their population. In this talk, I want to focus on the much bigger black holes, which is different beast. So first of all, kind of zooming out from our vantage point, in the middle of our galaxy, which is the Milky Way, there is a 4 million solar mass black hole. And just to be pedantic, I want to emphasize that we know the mass of this black hole to about 1% accuracy, and it's very, very heavy. Again, just to orient you, if you haven't imagined this in your head, this is the Milky Way. Well, actually, we can't take a picture of the Milky Way because we're inside it. So this is the Andromeda galaxy, which is our neighboring largest spiral galaxy. It looks like the Milky Way. And we are about 2/3 of the way out of the center. In the middle, this bright stuff is a nucleus of about 1 million stars, not a black hole. But in our own galaxy, there are observations of the very central point here. And then the way we know there's a big black hole there is that we have individual stars. These colorful things are just processed data on individual stars which are moving around. This particular point is the center of the galaxy. And I just like to emphasize this bar here, it says 0.05 arc second. So I don't know how many of you know, this is the unit of an angle. An arc second is, our whole sky is 180 degrees, each degree is 60 minutes, each minute is 60 seconds. This is 0.05 arc seconds. That's equivalent to 1.8 meters per person in somewhere at the distance of Johannesburg. If you look at him from here, from New York, that's an angle. So that's this angle here. So this is a crazy high resolution image. And then it's not even an image, it's actually a movie. This is 1995.5, so that's May or June of 1995. And you can actually see these stars moving as time passes. They follow orbits, which are extremely precisely described by almost high school equations of Newtonian ellipses. So all these, and the focal point of all these ellipses are here, so they're all moving around this point. And then if I can show one equation, actually if you forgot this, it doesn't matter, but if you still remember, because I want to make the point how we know that there's a very massive object there. There's a gravitational force, which was the inverse square law. So if there are two point masses, the big black hole and the star is going around, the force pulling the star towards the black hole is gmm over r squared, proportional to 1 over the distance squared. Newton's law of motion, that I'm sure most of you remember, F equals ma, and the acceleration is v squared over r. So that's all. I'm not going to show more equations. But if you equate these two, you find that you can rearrange these two, equate these two to obtain acceleration as a function of these masses. And what you get is the black hole mass is rv squared over the Newton's constant. This just says r is the distance of a star from a black hole, so you know that from this image. This is the distance. And then you can measure the velocity, or at least two components on the sky. And in fact, if you have spectrum, you can do the third component. So if there's a large, so this tells you the mass enclosed. And v, you can see large velocities imply there must be a large mass. So this exercise was done, that's how we know this very large mass, because these stars are going like crazy. They're going very, very fast. Something like, I don't know, maybe a few percent of speed of light. Okay, what about, so you could ask already, how did this big black hole get there, and why is it there, and how did it form, and when? Well, we actually cannot really tell that, because a black hole just has a mass, basically. If it's spinning, it also has a spin, but that's it. It doesn't tell you anything about itself. Unlike a star, which you can take a spectrum, or it changes with time, a black hole is just a point with a mass and possibly a spin. So it doesn't tell you anything about its history. So how do we get at this question? Well, obvious thing to do is look at census of other galaxies and in the distant universe. So what about other galaxies? Well, nearby galaxies, you can take images, you can even take spectra, and you can measure. You can't do this exercise because you can't see individual stars really close to the center going around. The angle is too small. But because the galaxies are farther, but you can measure the cumulative velocity using the Doppler shift of the combined light of either many stars, or sometimes just if there's some gas in the middle of the galaxy. And you do the same equation, basically. If the gas or the stars, statistically, they go around very fast, you know there's a big black hole. This can only be done for about 100 galaxies, out to maybe a few hundred million light years from us. And we have found that every time you can actually do this exercise, because you have good enough data on these galaxies, there's a black hole between 1 million and 1 billion solar masses. So apparently this is a common phenomenon. Galaxies have big black holes in their center. In fact, they even correlate. Bigger galaxies have bigger black holes. Okay, so that's where we are. Now, what about even more distant galaxies? So we can just zoom in all the way now to this edge of the universe, as I said. So we can't do this exercise to very far away objects, but we actually know that there are black holes in very distant galaxies. So this is just to be up to date. As you know, the James Webb Space Telescope was launched a year and a half ago, started delivering science. I assume I don't have to explain what the James Webb Space Telescope is. It's the successor of the Hubble. This image is, to my knowledge, is the deepest one that is, so you have to expose for a long time to get very deep images. It used to be Hubble was the record holder for 10 or 15 years, but now James Webb has deeper images. This is a tiny area of the sky, but there are galaxies and quasars out there out to about a look-back time of this 13.4 billion years. Most objects in this image are actually not stars. If you look up on the sky, you see mostly stars in our galaxy. But this area is so small, there's basically not a single star in there. But there are many, many very distant galaxies. Now, I say quasars, and that's the key for this talk. So quasar is what I alluded to earlier. A quasar is if there's a black hole in the middle of the galaxy, and there's enough material to fuel it at a high enough rate to become very bright, then we can actually see this object out to extremely high distance. So somewhat ironically, it's a black hole, but it turns out it's a black hole, but it's actually the brightest object that we can, brightest steadily emitting object in the universe. In fact, just for comparison, actually we're in this kind of a laboratory here which does particle physics, so it's good to remind you the energies involved. So, for example, a nuclear fusion in a bomb, nuclear bomb, or in the sun, which is powered by nuclear fusion, when you take two atoms and you fuse them together, you liberate nuclear binding energies, and those are of order million electron volt per nucleon. Now, the rest mass of a rest mass of a particle, a proton, for example, is about 1,000 electron volts. So 1,000 million electron volts, so a factor of 1,000 larger. Now, if these particles are falling to the black hole here, somehow and swirling around and falling in, and if some decent fraction of their rest mass energy comes out into radiation, which you can ask me later how it's converted into radiation, but you can tap that energy, that's several hundred times brighter than nuclear energy. So this is an extremely efficient power source, a black hole. In fact, can be 100 times brighter than nuclearly powered devices like a star or a bomb. It's a point on the sky. Usually you can't resolve this thing, so historically it's called a quasi-stellar object until people realized it's not a star. It's something else, very distant big black hole. And the key point is that because of this, we can see quasars to extremely large distances, including among the record holders as the most distant objects are these quasars. So there you go. Now we know that these billion solar mass black holes were already present the first 2 or 3% of the lifetime of the universe. And so now the question is, how does that happen? So this was kind of introduction, and I'm going to be a little more technical and focus on my own work here. But basically, I have to explain to you why this is surprising and what you might do to make such big black holes. Now, if I were just to ask you how you can make a big black hole, we could have a fun conversation about it, and you would probably come up with the 3 ways, which I wrote here. Well, we have some kind of gas cloud. It's 1 million solar masses. Maybe it just collapses to a black hole. Or, well, we know we have stellar mass black holes. I just explained to you that that's well understood. And there were stars in the early universe. So, and they died very quickly. So there were stellar mass black holes in the very early universe. Maybe they grew by accretion. Accretion means this process of fueling, sucking in the fuel usually through this configuration. So you can try to grow a single black hole. Or we know there are potentially many black holes, not just one in the early universe, and maybe they merge together and they make one big black hole. So these are the ways. Now, it turns out that all 3 of these are very problematic if you even start to add a little bit of physics and detail to this. So the reason you cannot just collapse 1 million solar mass cloud of gas into a single black hole is, well, maybe if it was completely mathematically a sphere and completely radially oriented inward, maybe it would collapse to a black hole. Although there are complications of that which I'll get to in a second. But the universe is never like that. I mean, the clouds will be inhomogeneous and not exactly spherical. So it's collapsing in an inhomogeneous fashion, and then it crucially also radiates and cools, which I'll get to in more detail, and then it tends to just fragment into small clumps and not a single body. The second option, I'll explain also in detail in a second, but it's actually not really possible, at least in first way of thinking about it, a very high rate of accretion. In order to take a 10 solar mass of black hole and grow it to 1 billion solar masses, you'd have to grow by a factor of 100 million, and therefore you'd have to accrete very rapidly. And I'll explain that that's not really easy to arrange. Black holes accrete at a lower rate due to their feedback, which I'll explain. Now the mergers also have a problem. Basically, these mergers are probably too rare, because in order to take 2 black holes and merge them, you need some mechanism to bring them extremely close to each other, and it's not obvious that should happen. So these are the problems. You have to think harder, at least harder than the first thoughts you have. And I was trying to come up with a scheme of, or kind of broad brush explanation, but the way you get around these problems is that the universe in the early times was actually quite different from the present day, and most of all, it was much more dense, because as you know, the universe expands. So when you look back in the early universe, it was compactified and much more dense. Then there were many small proto-galaxies which formed at very early times, which helps to get an early head start. And then, crucially, also the gas in the universe was chemically very primitive. So I'll explain why this helped. So to again, just to set the background to this discussion, I have to, in 1 minute, tell you the entire history of the universe, which only a few things matter. But this is the Big Bang here at time t equals 0. At which point somehow very tiny fluctuations were imprinted in the otherwise homogeneous universe. Then the universe expanded. This is here the present day. we have information about the universe when it was 300,000 years old. And I hope you heard about this. This is the afterglow of the Big Bang. It's emanating from a surface when the universe was very young, only 300,000 years old. And from this data on the so-called cosmic microwave background, we know the state of the universe at that moment was that it was basically completely homogeneous. There were no stars or galaxies. There were fluctuations, but only at the level of one part in 100,000 in density. So there were some variations in density across the universe, but by tiny amount. Here we have very much difficulty collecting any data because here we have to start from our Earth and look out from this direction and try to find very distant things. The record holder, as I said, is the James Webb. So we have some galaxies we've discovered when the universe is 100 million years old. In between is sometimes it's called the cosmic dark age. And then these are ground-based observations and rich astronomical data sets. So somewhere in between here, these fluctuations grew in amplitude and they somehow started to form galaxies or some structures. Okay, so how did that happen? So in order to form a galaxy out of this expanding universe, you have to have a part of the universe which stops expanding with the rest and then collapses back on itself. And I won't have time to dwell on this, but as you probably also know, most of the gravity of the universe is provided by dark matter. So in fact, it's the dark matter fluctuations that grow mostly and become detached from the expanding universe and collapse back on themselves. And you have dark matter, clumps of dark matter, which pull in some gas with it, with the dark matter. And now, now you could in principle have what you call a galaxy. But the gas that you're trying to compress into this so-called galaxy, just basically better to think of it as a collapsing cloud of gas. It tends to get very hot because you're compressing it. By my very clever analogy here, I showed a bicycle pump, and as you know, if you compress the air in the pump, it gets very hot in the bottom. But if you compress something by its own gravity, it's the same thing. It tends to heat up just because you compressed it. So then the pressure builds up and it would halt the collapse. Now, the first time when things are big enough that they can actually collapse in the face of this pressure is roughly when there's about 100,000 or a million solar mass worth of gas. This just follows from some theory, but I can explain if you like later. So these, I actually call these microgalaxies because the Milky Way is 10 to the 12 solar masses, so this is 10 to the minus 6 of a Milky Way. But this is just a collapsed cloud of gas. There's no stars or anything yet. It's just a cloud collapsed under its own gravity because it was big enough to overcome this pressure. But then, eventually, this cloud should form stars. So the only way to do that is this cloud has to radiate away its internal energy and deflate its pressure continuously, so that when you keep collapsing it, the gas keeps collapsing, the pressure doesn't rise. You just keep it in check. So this is actually very well known. This is what happens in our universe. For example, to form a star in our galaxy, there's some clump of gas, which we call a molecular cloud, and then it's collapsing under its own gravity. And then the process that helps you form a star is that the gas cloud, the molecular cloud, has various elements in it. The most important one is actually CO molecule, and this is a picture of a molecule. And if you remember anything about molecules, you know they can vibrate and rotate, and that they have energy states from quantum mechanics. So you can take a molecule and you can bump it into another molecule, and this molecule can vibrate differently in a state which is slightly higher energy. And then very soon afterwards, the molecule can decide to go back to its previous state and emit a photon. Does that make sense? Hopefully. So this process is continuously, collisions are happening all the time. You're exciting these quantum levels of molecules all the time. They decay radiatively, they emit photons, and these photons leave the cloud. So this is a way to convert the motions of the particles of the plasma to photons which leave. So this is called cooling in astrophysics. This cooling is very efficient and takes the gas down to basically a few Kelvin, almost absolute zero, because these molecules are very complicated. And well, maybe just in case you... so temperature is equivalent to energy, because temperature is nothing more than the speed at which the constituent atoms are moving around. So you can think of it as average kinetic energy per particle. So because the energy levels are in these complicated molecules are very small spaced, they're very low lying levels. So even if you bump into each other at these tiny speeds, you still can radiate. So the gas gets very cold. Now, okay, this is the periodic table of elements. And as I said, carbon and oxygen are the most important molecules causing star formation in our galaxy. But I'm sure you also realize that in the early universe, the periodic table looked like this. Because I'm sure you know, you've heard this, that every other element pretty much in this periodic table was synthesized in stars. After stars go and die as supernova, all the nuclear fusion that happened inside the stars, they produce these heavier elements which get ejected and pollute the rest of the universe. But in the early universe, the first clouds that collapse, we just have hydrogen and helium. That comes from the Big Bang. It got fused in the Big Bang itself. Okay, but these are extremely simple atoms. It's just a hydrogen atom and a helium atom, so they cannot be excited to these states and radiate, which means the gas cannot collapse further. Unless, well, you actually still can excite levels. So for example, the hydrogen atom, for those of you who still remember, it's a proton and electron. And the electron is extremely simple. It's just basically you can think of it as a planet and a star. The proton is in the middle, the electron is going around, but it also has energy levels. So you can take two hydrogen atoms, collide it, and raise it to a higher level. And then you can go back radiatively. But the first level of a hydrogen atom is at 10 eV. So that's 10,000 times more energy is required to excite a hydrogen atom than a CO molecule, which means this cannot cool the gas down below 10,000 degrees. So if this is the only cooling agent available, all these primordial proto-galaxies would be extremely hot compared to a star-forming cloud. And now I come to some very important detail which is dear to my heart, because even my PhD I worked on that. So the H2 molecules can form in principle, because it doesn't require any other element. You just take two hydrogen atoms, you can make a hydrogen molecule. And that's a little more complicated, the hydrogen atom, and it does have some lower levels. It's kind of in between. The lowest level of an H2 in order to cause excitation is a 0.1 eV, so you can actually cool down to 100 Kelvin, so it's kind of warm. You can think of this as, in present-day universe, star-forming molecular clouds are very cold. Pristine H2-free proto-galaxies would be very hot, and these would be kind of warm. Now this leads to completely different behavior of what happens in this collapsing cloud. And I just like to point out, at the very basic level, it's kind of ironic that if you want to know the fate of the first object in the universe, it's really determined by the H2 molecule. So that's to be appreciated. Now, why does this temperature matter? So I think you've probably also seen pictures of this. This is the structure of the universe. This is just, let's say, the dark matter density, but also the gas density. This is called a cosmic web. This is a well-known structure. In fact, in my opening slide, you see this observationally. The universe looks like this. So the galaxies would be the knots in this cosmic web. And you can do detailed simulations of how this structure grew from the seed perturbations at the Big Bang. And you find the first galaxies, which form at the knots of these. So this is just a zoom in, which is from our own simulations. But you basically have a cloud. There's filaments connecting it to the rest of the universe, and gas is flowing in and heating up. Sorry, I promise no more equations, but one more equation is that the rate at which the gas flows in here goes like the temperature to the 3/2 power. This is kind of counterintuitive. Forget the middle part here. But this says that if you have a cloud that's warmer, it's actually collapsing faster. It's kind of counterintuitive because I said pressure hinders the collapse. But in fact, the correct way of thinking about it is the pressure is a barrier to collapse until you build up enough gravity. It means you have to have if you have more pressure, you need more gravity. So you need a bigger object to collapse. But once you have the bigger object, it will collapse much faster, because the collapse happens at the sound speed, and the sound speed is higher for hotter gas. So this means the collapse of this gas cloud towards the center is going to be much faster if you raise the temperature. So that you can already see we're getting something interesting, because in normal star-forming molecular cloud, you form stellar stars. But now we're going to have potentially much more rapid inflow into these centers of these clouds. And so I want to contrast the three options here. So present-day universe, this cartoon represents present-day universe, a warm, typical maybe protogalaxy, and a rare case which gets hot because there's no molecular hydrogen. In the first case, you cool down to a few Kelvin. You can calculate from your theory, this should be the accretion rate. 10 to minus 5 solar mass will fall every year to the center. And the result of this is that you form a normal star, and with a distribution of masses, and you have a 0.1% chance of such a star becoming a black hole at the end, because 0.1% of the stars have masses above 25 solar masses. So that's a very well-known paradigm in our nearby universe. Now, if this temperature is stuck at a few hundred Kelvin, this inflow rate will be 100 times higher, and you form much more massive stars. So that's kind of good news for us, because we want to make black holes. So it's pretty much all these stars. They actually have a jargon name. They're called population 3 stars, if some people in this room know about those. So these so-called POP3 stars, which are formed out of pure hydrogen-helium clouds, the first stars in the universe, they will be all very massive, and basically roughly half of them will be massive enough to leave a black hole remnant. But we actually want big black holes, so there's even bigger news with this option. So you can actually ask the question, why does this end at 100 solar masses? What if this accretion just keeps going? Why don't you grow the star even bigger? And the answer to that, in fact, this is also well known. In our own galaxy, the most massive, I mean, this is the typical range, but the most massive stars are about 100 solar masses. The reason for that is that once you form the star, it starts shining, ultraviolet radiation, and shuts off the flow of material that's falling on the star. So it can never grow above 100. So it's a self-limiting, it's a feedback that keeps the stars from getting bigger. That also happens here. So you get more massive stars, but they stop at 100 solar masses. Now, suppose you manage to make a protogalaxy where you wiped out the molecular hydrogen. Just for sake of argument, let's say that for some reason happened. Now you have a gas cloud that's 10,000 degrees. The inflow rate, it has to be actually slightly bigger than this one, so that gravity can operate and cause the collapse. But then it's going to be very rapid, 10,000 degrees, and then there is a key difference between these two, which is this star. You can still think of it as you're trying to make a star. You have what we would call a protostellar core. It hasn't turned on nuclear fusion yet. It's trying to, but then it's gaining the next layer so rapidly from the surrounding gas that it's actually growing faster than it's collapsing to turn on the nuclear fusion. So it just keeps growing up to about 1 million solar masses. And at that point, there's a well-known an instability, which is known for 50 years from general relativity theory, that 1 million solar mass star becomes unstable and just collapses, and most of the material ends up in the black hole. So So this sounds like a very exotic object. It's sometimes called a supermassive star, but it would form in this cloud, and it would leave behind this big black hole remnant. So that's great. In fact, it would solve our problem because we would get a black hole in one shot, essentially, after a few million years. Now, why would this happen? I think I cannot really squeeze into this lecture how you realize this. This meaning you have to wipe out the molecular hydrogen. The answer is that we don't know. Various ideas have been proposed, but probably the best idea is that this happens in a rare case, maybe 10⁻⁴ of all protogalaxies. It has a neighbor. They're collapsing at the same time. So protogalaxy forms here, another one just maybe a million years behind over here. So the first one collapses, starts emitting radiation, shines on the second one, and you can use UV light to destroy the molecules. So now this second cloud, because of its neighbor just formed nearby just before it, it can be in this regime. So that's a way to produce this situation. Okay, I hope this was clear enough. It was detailed, but that is the leading idea, I think, for how to solve this problem. So we have a way to get around this. Basically, you have to have an H2-free protogalaxy, which is very unusual, but produces very rapid inflow, and the supermassive star and the supermassive black hole remnant. Okay. Now the second one I can actually do pretty quickly because it essentially relies on the same idea. So, as I said, okay, the most protogalaxies failed this, and they had some molecular hydrogen, and they made a 100 solar mass black hole from the star in that cloud, and that black hole could start accreting and growing. And you can ask, well, why doesn't that grow into a supermassive one black hole that we would want? So the reason for this is actually very well known also, or has been understood for a while. So suppose here is my stellar mass black hole. Let's say this is the first generation star, 100 solar mass black hole is left behind, it's accreting. So it's basically like a quasar, but it's scaled down to a stellar size. And material is falling in. Now this quasar then is going to shine very bright, right? This mini quasar or micro quasar. Oops. So that means radiation is emanating from the object as the material is trying to fall in. And in fact, the more rapidly you assume that the stuff is trying to fall in, the brighter the radiation. And it turns out this process leads to, if you do the mathematics behind this, it's very simple actually. I even have a derivation if you want to see it. The end result of this is that there's a universal maximum feeding rate. And this is, I like to just, instead of showing you the equations, the analogy is if you have your baby and you try to feed it dinner, if you do it very slowly, it will all go in. Then you try to make it faster and faster and faster, and then you reach a rate at which it's no longer going in. It's exactly the same here. You try to feed the black hole, you reach a limit where the radiation is so strong that it annuls the gravity, which is the radiation is impinging on the infalling gas, puts radiation pressure on it, pushing it out, and it counteracts gravity, and you cannot fall in anymore. And it turns out that this feeding rate, if at this max, this is called the Eddington rate, actually because Eddington 100 years ago realized that this is also for stars the case. So stars actually shine at this luminosity, the Eddington luminosity. For their mass, they're emitting just enough radiation not to balance the gravity. They cannot be brighter. So this is a historical name, but it applies to black holes. And now there's actually a way, we discovered recently, a few years ago, that there's actually a way to get around this limit, which if I wanted to be very crude, I could just kill the punchline and say, well, but if you force feed even faster, 100 times faster, it actually goes in. But that's very rude, but that's actually what happens. So here's a picture of what I just described. Here's the black hole. This is the cloud of gas now from sideways. This gas is falling towards the black hole. This is the gas further out. And this represents a photon that was emitted from the middle, from the bottom, the black hole vicinity, this photon actually cannot just go straight out. If it didn't interact with the material, it wouldn't be no problem. So by definition, this photon is actually random walking. It's scattering on electrons here, and it's just bouncing around and eventually finds its way out. And then at some point pushes the material in the process and stops the accretion. Now suppose you crank up your externally driven accretion rate here at the end. So you feed it extremely rapidly. You build up a very, very high density here. And then some new phenomena happens, which is the photons cannot make it out of the cloud in the middle. Because essentially, well, maybe I won't go into the math here, but basically there's an effective rate at which the photon is making it out, which is not the speed of light, because this is a random walk. So this is actually radially outward velocity on average is much smaller than the speed of light. And then if this gas is actually falling in faster than this outward diffusion rate, then these photons never make it out. They'll be swept into the black hole with the material. I guess another analogy here would be this is like fish trying to swim upriver. If the river is faster than the fish's speed, the fish just keeps going backwards. So you effectively add to some, generally the inflow velocity of the gas increases, so it's high here, lower here. So there's some surface here, inside of which you could even think of it as a horizon. The photons can never get out. This is not because of relativity, it's because the gas is sweeping them in too fast. And if you eliminate from our view all the photons that were emitted here, you basically can kill most of this radiation because, sorry, one more equation. Gm over R is the potential energy. So you know that 1 over R is the energy you're liberating. If you put a proton that's falling in, it's accelerating, and if most of the energy is generated in the middle or in the bottom of this system. So if you cut out this part, you just kill the radiation, most of it. So it turns out if your inflow speed is about 500 times this critical rate, we found, then this feedback no longer operates and just the black hole just swallows everything. So this is a new regime, and it turns out that it kind of agrees. If you go back to this picture and you take this accretion rate generated for a 10,000 degree cloud, that's not obvious from the numbers I showed, but that's in this regime where you trap most of the radiation. Very good. So now we solved our second problem. You can actually take a single stellar mass black hole. If you have this rapid inflow of a very hot gas, it will actually, despite this feedback, it will actually grow very rapidly. So that's a possibility. And then let me come to my last option, which is merger. So suppose everything I said is wrong. As I said, these are all speculations, because somehow this H2 is still there and you can never have this rapid gas collapse. We still have this third idea that you can have lots of mergers. So this is another solid part of this theory, which is we know galaxies are built up by mergers. We actually, well, if you go back to several slides here, I don't have a movie, but this picture is actually a movie, and this entire structure is evolving. And like, for example, this galaxy here and this galaxy here, probably in a few 100 million years will merge into a single galaxy. As the universe is expanding, the dense parts separate from the expansion and approach each other, and they keep merging. And we see this is very well developed theory, and also in observations we see galaxies which are colliding quite obviously. These ones passed near each other, this so famous antenna galaxy, because this tidal tail resulted from a close passage. Now, if galaxies, and if in the early universe the proto-galaxies are doing the same, well, that's theory. We don't have observations of those directly, but presumably we think they do the same. They merge a lot. So then we have our proposed new solution, which is you have these solitary early stars in the centers of proto-galaxies. They're growing at a rate which is not enough to grow them into supermassive black holes. But then these protogalaxies merge, and the black holes in them can also merge. And then you can keep building a big black hole this way. So that sounds nice idea, but can two black holes really merge? And so here we again have a problem, and this is that, well, why would two black holes merge? So there's one obvious reason, which is completely inevitable, which is the emission of gravitational waves, which I already said in the beginning was experimentally confirmed by the LIGO experiment and detected on Earth-based laboratories. But the simple way of thinking about it, here's a black hole, here's another black hole. Now, if they go around each other, then they're sitting in the bottom here and they're disturbing space-time and emitting these waves. These waves carry energy. You can't have for free these waves. And this energy comes at the expense of the orbit. So the orbit must be shrinking. This is very well known. We've seen it in the LIGO experiment. The first Nobel Prize for a pulsar was given because we saw two pulsars shrinking their orbit. So this is an inevitable way to take two black holes and eventually they'll merge. But what I like to point out is, okay, that's nice, but how close should they be that they should merge in a reasonable amount of time, let's say the age of the universe. So this process of emitting gravitational waves is extremely steep function of the separation. If you take two black holes and put them very far, yes, they'll emit gravitational waves, but it will be very weak. And will take Googleplex years to actually merge. If you put them very close, the waves become very strong, and the process of merger will take short time. So you can ask the question, how far should they be so that they merge in 10 billion years, let's say. So that depends on the mass. So if you take two 10 solar mass black holes and you want them to merge in 10 billion years, they have to be 0.1 AU apart. And AU is the Earth-Sun distance. So now you're asking, if you want stellar mass black holes to merge, you want them, two black holes 10 times the mass of the Sun. They should be 10 times closer than the Earth is to the Sun. So that's clearly not natural thing to happen. Maybe randomly sometimes happens, but not natural. Even worse, if you want 10 to the 6 solar mass black holes to merge, they should be a milliparsec away from each other. So now you're asking a black hole like the one in the center of our galaxy, there should be another one next to it, same mass, and the distance between them should be roughly 1,000th times smaller than the typical distance between two stars. So clearly very abnormal situation. So people have thought about this. Actually, this is sometimes called the final parsec problem, because if you think of even bigger black holes, 10 to the 9 or 10 solar mass, then in order to merge they have to be 1 parsec apart. So this problem of not being able to merge has a name. It's called the final parsec. You have to somehow get to the parsec separation to merge these two big black holes. In the beginning of the process you'll have to be even closer. So I can go very quickly because the solution we propose to this is actually very simple conceptually, which is, well, I just said that these black holes don't live in vacuum. This whole analysis here assumes you have empty universe and two black holes. That's clearly not the case. In these protogalaxies, there's dense gas surrounding the black holes. And you have to ask yourself what happens if the same dance of the two black holes occurs embedded in a dense gas cloud. So we've been doing a lot of work on this, and these are based on hydrodynamical simulations. But the point is very simple. This is basically what happens. So this is an image from a movie where there are two black holes placed in this simulation, and this is a plasma which has been assumed to have collapsed into a disk and is going around in a circular fashion around the black holes. And then red here means dense, and yellow and white means low density. And this is actually a movie. So you can see that these there's actually very much to say. I sometimes give 1 hour talk on just this picture, because there's lots of interesting points, like even the emission is different from a single black hole quasar, and it's periodic behavior. But from our purposes here, the point is that you create this cavity, and this thing here is not axisymmetric. You can see that the gas is just not concentric around these 2 point masses, which means if you simply sum up the gravitation forces, you take this piece of gas here, it's pulling this black hole and also this black hole in different directions. If you sum up all this gravitational tugging, you find that they exert a torque. They remove energy and angular. They basically remove angular momentum from the binary black hole and make them and push them together. This turns out a really subtle problem, and in fact there were lots of discussions even up to last year among astrophysicists whether this gas cloud is pushing the black holes apart or pushing them inward. But it seems now converged that numerically that this gas cloud is actually pushing the black holes in, and that's the solution potentially. Oh, actually, just to brag, this picture is not so uncontroversial. It was on Link NYC. So the solution to the last problem is, because of the gas, the two black holes will spiral in maybe a few 100 million years, reach this gravitational wave regime, and then they merge. So these were my 3 ideas, and this is my. I don't know how I'm doing on time, but I thought this will probably be the end. I can keep going, but the last big question is how are we going to figure out which of these 3 things actually happened in the universe, or most likely all of these could be important. And I just have a very broad brush conclusion here about that. I can go into some more detail, but it's basically you should look for signs of mergers between very distant black holes to probe this idea that they keep merging. Or you should look for accretion onto black holes to see they're growing by accretion. So mergers, the best way to look will be, sadly only 10 years from now, there will be a new instrument called LISA. So this is very similar to the LIGO instrument, which again I assume that people know. Basically an interferometer which measures the distance between 3 masses and looks for gravitational waves. Unfortunately, LIGO is sitting on the Earth, and the Earth is seismically very active, so you cannot do any low frequency vibrations. You just see the trains going by 15 miles away. You won't see black holes in the universe. But if you put this in space, there's no vibrations, and I should say the big black holes involve larger distances, and so they have longer orbital periods and lower frequencies. So if you want to see the big black holes in gravitational waves, you have to go to low frequency and space. So LISA is mostly a European Space Agency project to be launched. It was actually approved on last Monday. And it's about €1 billion, and it's supposed to launch in 10 years. And is very sensitive, so you will easily see the mergers between, let's say, 2 black holes, 10 to the 4 solar masses when the universe was just 50 million years old. It will be visible. The other thing you should see is look for small black holes very far away and try to build up a sample and study how they grew over time, not individually, but the population. And the James Webb can actually make some strides about this. It's now detected black holes that are about 100 times smaller in mass than we previously had, maybe 10 to the 6 or 7 solar masses. And it looks like they actually favor the first option that I described because the host galaxy of the quasar black hole is unusually small. So usually the black hole, like in our Milky Way, is much smaller than the galaxy. Whereas in the picture I described, most of the gas cloud ends up in a black hole. And that means there's a characteristic difference in that scenario, which is the black hole is much bigger than the galaxy. So there's some hints for that, but we need to go lower mass black hole and farther away. The best would actually be an X-ray telescope, because most of the emission from these smaller black holes comes out in the X-rays. So there's some plans by NASA to build an X-ray telescope. and go after those. Maybe the last thing I should say is you can actually look in the nearby universe or for signs of binary quasars, just for some evidence that there are actually black holes which are merging. I thought I won't have time to talk about that, but what is the time? Should we?
1 minute.
So 1 minute. Okay, but then I will show you just one picture. 1 minute I can do in 1 minute, just because this is your latest paper is always the most exciting. So the idea here is that, well, maybe there's some evidence if black holes are actually merging. We can actually look with a normal telescope and look for signs of it. And you all know how a black hole looks like. I actually used to give this talk and show this picture from Interstellar. And you know, if you've seen the movie, that because of gravitational lensing, a black hole, which I showed the quasar disk, actually doesn't appear like that, laminar. Because the photon's trajectories are bent around, it will look like this. Now we actually have images of this from a radio interferometer observations. So these are actual data of black hole images. So the very simple thing we pointed out, so these are not technical slides from my paper, but we have something really trivial. Well, if there's two black holes, both of them will look like that internally, plus there's a decent chance that one black hole will go behind the other, and there will be lensing effects. So it's like you have an interstellarized looking image, there's an interstellarized looking other image, and then there's also an interstellarization from the fact that the light from this is lensed by this. So here's our beautiful movie where you see such a thing, and you see some very funky images. The sad thing is you can't actually resolve this with a telescope because these will be tiny, but you can integrate the total light and just see how bright this thing is if you just see it as a point and ignore all the text. This is just a sequence of 3 snapshots around this conjunction, and what you see is very kind of obvious. You have periodic flares. Every time one black hole goes behind the other, you have a flare. And moreover, if the shadowy part is behind the black hole, then you have a dip. Because now you're trying to amplify the non-existing emission in the middle. So at least, maybe as an example, there's a few more of these, but one example is you should look for quasars that have periodic flares with dips in the middle. For this you need many quasars and look for high cadence time series data, but that's doable in the future. So I will stop there. There's some other ways to look for at least these mergers. And these are my take-home messages. Very quickly, the black holes exist. They're very large in the middle of galaxies, and their seeds were placed in place very early on. We came up with some ways to maybe make these big black holes relying on rapid gas collapse in some unusual H2 molecule-free protogalaxies or through mergers. And to be honest, to figure this out will take a while. I think we need some new data and maybe some more ideas from what diagnostics to look for. So that's it. I'll stop there. Thank you.